So welcome to today's lesson on nuclear fission and nuclear fusion. So in terms of the specification, you have to have an understanding of both nuclear fission and fusion and how they're both sources of energy. Understand the process of nuclear fission involving the fission of uranium-235 and it producing two daughter nuclides. Okay, so you have a deep understanding of the actual process. Understand there's a chain reaction also involved in nuclear fission, at least with uranium-235. Understand the role played by control and moderator rods in nuclear fission reactors. Understand the role of shielding also around the nuclear reactor and why that's important. Differentiate between nuclear fusion and nuclear fission, and describe nuclear fusion as well as nuclear fission, so both of them, describe nuclear fission and fusion. And know that fusion is a source of energy in the stars, so our sun uses it as its source of energy. And finally, explain why nuclear fusion doesn't happen unless it's high pressure and high temperature. So let's now focus first on nuclear fission. So nuclear fission, basically it's the splitting up of an atomic nucleus, and it was first discovered by three scientists in 1938. Lise Meitner, Otto Hahn, and Fritz Strassmann. So in terms of nuclear fission, the first thing you got to do is find a nucleotide, a nuclide that can undergo nuclear fission. This is known as fissile material, and the most common one is uranium-235, which splits to form fission fragments. And they can be neutrons, gamma radiation, a lot of energy, and daughter nuclides. So in terms of the nuclear equations, what happens is that uranium-235 is bombarded with a slow-moving neutron to form the unstable isotope of uranium-236. And then that uranium-236 pretty much instantaneously begins to divide into two daughter nuclides, barium-144 and krypton-89, and three neutrons and a lot of gamma radiation and energy. There are other examples that can happen in nuclear fission. So other fissile materials can be uranium-236, which basically splits into xenon-134 and strontium-90, with two neutrons being formed this time, and again lots of radiation. Or more commonly now, plutonium-239, which also undergoes fission to form cesium-137 and deuterium-89. And also three neutrons and gamma radiation. So an important part of the process of nuclear fission is the chain reaction component. Okay, so in nuclear bombs, the chain reaction is out of control, and in nuclear reactors, it's controlled. So basically what happens is once one uranium-235 nucleotide or nuclide undergoes fission, adjacent ones will undergo fission as they're bombarded by the neutrons that are formed by the original fission event. So just to summarize, in nuclear fission, what happens is that we have fissile material, for example, uranium-235, and a slow-moving neutron is absorbed into that nucleus. This causes the uranium-235 to turn into uranium-236, which is an unstable nucleus. So because it's unstable, it starts to oscillate and begins to break up, which releases energy and three neutrons, along with the two daughter nuclides. You can see also the chain reaction process. As the neutrons get released, they hit adjacent nuclides of uranium-235, and that initiates the process of the chain reaction. So an example of an uncontrolled nuclear reaction in terms of fission is the bomb that was dropped in Hiroshima in 1945. This is it here, little boy, which is the uranium. So basically the fissile material was uranium, okay? And what happened is that essentially it was dropped on December 1945, August the 4th, 1945. And 150,000 people died. And it wasn't actually being tested in a way. It hadn't been tested yet, so we didn't actually know what would happen. Some scientists thought that, well, maybe it will actually explode and destroy the entire universe. We weren't sure. And then a day later, the plutonium-based nuclear bomb where plutonium was the fissile material, was dropped on Nagasaki. And in Nagasaki, about 39,000 people died initially, and 25,000 were badly burned and injured. So this was Nagasaki 2 days before the explosion, and this was Nagasaki 3 days after the explosion. You can see, essentially, it was wiped clean. There was no buildings left, basically. It was all destroyed. The power of nuclear energy. So Nagasaki's actual explosion device, the nuclear bomb, was dropped 11 miles above Nagasaki and exploded. The mushroom cloud went up about 11 miles high, a massive explosion. Okay, you can see here that the ground zero, where it's orange, there was the fire and blast damage, and where it's yellow, there's only blast damage. The reason why it has that kind of shape is because Nagasaki is actually in a valley, so the flames or the nuclear explosion and heat went down that valley. In the next few slides, I'm just going to show some of the physical effects on humans, on the people of Nagasaki. So I warn you that some of this content is rather visual in terms of what it actually portrays. So there's a warning there. Okay. So here you got 3rd-degree burns on the people of Nagasaki, a lot of burns, a large number of burns, and that obviously secondary infection. People died of those burns. There's an example there of somebody really badly burnt. It's very graphic. Again, lots of burns, 3rd-degree burns. Their children starving because there's no food anymore due to the water not being there as well, to dehydration. And even in the 1970s, Japanese children were being born from parents who survived Nagasaki who still had genetic mutations. So that's an example of when nuclear fission is uncontrolled. Okay, and then we have when nuclear fission is controlled, and that's nuclear fission reactors. So nuclear fission reactions release a large amount of energy. The way they do this essentially is diagrammed here. So the nuclear fuel undergoes the nuclear fission reaction. It releases lots of energy. That energy is used to heat water, which turns into steam. That steam turns the turbine, which then acts on the generator, which creates electricity. That's the plan anyway. Inside the reactor itself, the reactor has fuel rods, which contain the uranium-235 or polonium-239, depending on the reactor. It also has moderator rods and control rods. Okay, so basically the control rods move up and down, and they control the amount of energy that's being released. It kind of slows up or speeds up the nuclear, slows down or speeds up the nuclear fission reaction occurring in the reactor. So how does it work? Yeah, so you have the uranium fuel rods, which are the source of the nuclear fission. Then you have the control rods, which are made of boron, because boron absorbs the neutrons, and that means that it slows down the nuclear chain reaction because it stops adjacent uranium-235 nuclides from undergoing fission. And we also have the graphite control rods, moderator rods, graphite moderator rods that surround the fuel rods and also slow down the neutrons as well. Okay. Then we have the coolants. Usually it's water, but also carbon dioxide can be used, carbon dioxide gas. We have the heat exchanger, which cools down the hot water so it can be recycled in the system. And we also have about a 2 meter to 3 meter concrete shield for the whole reactor. So if things get out of control, no gamma radiation is being released and no high-speed neutrons, or low-speed neutrons in fact, for that matter. Okay, so an example where it all kind of went wrong was in the Ukraine, in Pripyat. You might know it as Chernobyl, the nuclear station there. And what happened there was that the Russians tried to save a bit of money, and they basically used cheap control rods which had a graphite tip. Those graphite tips were not sufficient enough to control the chain reaction because boron's more expensive. So basically they tried to control the reaction, they added the control rods, but didn't work sufficiently, so there was an uncontrollable nuclear fission event and the reactor exploded. So that was nuclear fission. So the other one you have to do is nuclear fusion, other form of nuclear reaction. So what is nuclear fusion? Well, nuclear fusion is kind of the opposite, where nuclear fission is the splitting of an atom. Nuclear fusion is going to be when you're fusing them, joining together. Okay, and it produces, again, a massive amount of energy because it's basically the energy our star uses, the sun, okay, to produce energy. And the advantage too is that the products of this nuclear fusion, as opposed to the products of nuclear fission, are not radioactive. So this is basically a typical thermonuclear reaction in terms of nuclear fusion. So one hydrogen atom fuses with a deuterium atom to form helium-3. Okay, and that happens in stars as well. Okay, so nuclear fusion is basically the joining of these two atomic nuclei to form two electrons, high-speed electrons, and lots of energy. And the energy of fusion is basically used to power the sun, but it's also the source of the hydrogen bomb if it's uncontrolled. So finally, nuclear fusion reactors are a possibility in the future. The problem, of course, is that with nuclear fusion, you need a source which is going to be high temperature, the sun, and high pressure. So you need that high temperature and high pressure in order to push the nuclei together to make the helium and also allow that reaction to occur. So it's actually quite difficult at present to allow nuclear fusion to occur for large scales. The more energy is required to make the nuclear fusion reactor and let it run than you actually get out of the entire process.